All right, this is the video guide that goes along with the Unit 4 review for periodic table, periodic transnuclear chemistry. First one, it's asking how many valence electrons each of the following groups have. So we need to know the names of the groups. And so looking at this one, first it said alkali metals. Well, we know that alkali metals are group 1. Hydrogen is not one of them, so these. They all have, by definition, one valence electron. The next group is alkaline earth. Alkaline earth is group 2. Everything in group 2 has 2 valence. The next one is halogens. Halogens are over here. They're group 17. Everything in group 17 happens to have 7. Noble gases. The noble gases are over here, group 18. The noble gases happen to have 8 valence electrons. Group 13. Group 13 is going to be this one here. It starts with boron on down. They happen to have 3. And then group 16. Group 16 is over here with oxygen. These all happen to have 6. Oops, went the wrong way. Okay. How is the modern periodic table arranged today? It's by increasing atomic number. If you look at it, it is arranged in order of increasing atomic number. What patterns are observed in the arrangement of elements in the periodic table? They have repeating properties every 8 elements. So similar properties. Okay, which of these following sets of elements have similar chemical and physical properties? Well, in looking at these, oxygen, nitrogen, carbon, and boron, so if we look at those elements are right here. They're in the same period, but not in the same group or family. Probably not that one. Strontium, magnesium, calcium, beryllium. Okay, looking at those, well, lo and behold, they are in the same family. They're all alkaline earth metals. Probably a good choice. And then the last one is talking about nitrogen, nickel, and niobium. You look at those, well, they're kind of random. They're just ones that start with the letter N. So best choice for number 3 is B. Name 2 elements that have properties similar to that of calcium, and why did you choose these elements? So we got to look at calcium. Calcium's right here, so it's any of the other elements that are alkaline earth metals. So any of the following will count. So we'll say it could be beryllium, could be magnesium, could be strontium, could be barium, could be radium. Why? They're all members of the same family. They all have 2 valence electrons. So in problem 5 here, we are looking at the electrons in these 3 elements. We're basically drawing what's a Bohr model. And we're going to be calculating ZF, the effective nuclear charge. Thing you need to remember, so here's the formula for ZF. ZF is equal to Z minus S, where Z is the number of protons in the nucleus, S are the core electrons. And so looking at the periodic table and looking at silicon, silicon's right here, atomic number 14, that means it has 14 electrons. You'll recall the first row can have 2, and then the second ring can have 8. So there's a total of 10, which means we need 4 more. We're going to spread these guys out. And so there is a Bohr model for silicon. Now to calculate ZF, well, we know the atomic number is 14, and then you're going to subtract the core electrons. That's everything in the center, which happens to be 10. The ZF for silicon is 4 plus. Okay, for potassium, here's potassium, atomic number 19. And so there are going to be 19 electrons. So in the first row, or first ring, you're going to have 2, 8 in the second. And then it's going to also have 8 in the third. So right now we're at 18. There's your 19th one. Okay, so only 1 valence. ZF for potassium, total of 19 protons. 18 electrons are in the inner ring. The ZF for potassium is 1 plus. Okay, last one, oxygen. Let's take a look at oxygen here. Oxygen is atomic number 8. So in the first ring, 2 electrons. In the second, we got 6, 4, 5, 6. And so for the ZF for oxygen, total of 8 protons. There are 2 electrons, which gives us a ZF of 6 plus. So essentially, guys, ZF is always going to be equal to the number of valence electrons. And if you think about it, it makes sense, because what we're doing is taking the atomic number, which is equal to the number of electrons in the atom. The proton-electron number should be equal. And then if you take away all the core electrons, the ones in the center, the only thing left is the number of valence. But that's how you calculate ZF. Okay, so who arranged the periodic table in the format similar to what we see today? It's Dmitri Mendeleev. Okay, how did he arrange the elements in his table? He arranged them in groups of similar properties. And what was kind of revolutionary about Mendeleev's table is he left spaces for yet to be discovered elements. How is the modern periodic table arranged today? And we already kind of mentioned this, but increasing atomic number. And there's other ways you could answer. You could say, into groups and periods and all that stuff, but many different answers, but that's sufficient. Okay, which of these following elements have sets of similar chemical and physical properties? So in looking at these, we're trying to determine ones that are in the same group or the same family: lithium, beryllium, sodium, and magnesium. I mean, they're all metals, but they're not in the same group, so probably not that one. Chlorine, phosphorus, silicon, sulfur. Once again, chlorine, phosphorus, silicon, and sulfur, they're all in the same period, but not the same group or family. Oops, I went the wrong way. Cesium, potassium, rubidium, and sodium. There you go. Those are elements that are all alkali metals. They're all in the same group. They all have 1 valence electron. Best answer is C. Identify the following as either a metal, nonmetal, or a metalloid. So we have a series of elements here. Thing you have to remember, there is a line here that's called the stair step. Divides the table essentially into a few parts. Everything on this side over here is nonmetallic. In hydrogen also counts as a nonmetal. Everything to the left side is said to be metallic, even the lanthanides and actinides down here. And then things that are touching that stair step with a side are considered to be metalloids. They're not metals, they're not nonmetals, they're in between. The one exception is aluminum. Aluminum, even though it's touching with a side, is a metal, and you guys know that. So, cobalt, let's take a look. Cobalt is right here, definitely a metal. Silicon. Silicon is sitting on the stairs. We're going to say that's a metalloid. And then phosphorus. Went the wrong way. Phosphorus, not touching the stair step, it's to the right. That's going to be a nonmetal. Potassium is right here. Okay, definitely to the left. That is a metal. And then hydrogen, even though hydrogen is on the left side, it is a nonmetal. So it is not an alkali metal. It's up here kind of on its own. So we're going to say hydrogen is a nonmetal. Okay, and so now we're looking at properties. Do these explain properties of a metal or a nonmetal? So first one says gas at room temperature. Well, most of the gases are going to be on the far right side of the table, like the noble gases. So that is nonmetallic. 1 to 3 valence electrons. Well, looking at the table, these have 1, these have 2, these have 3. That's definitely explaining a metal. Malleable. Malleable is a scientific word for bendy, or you can pound it into shapes. That is a metallic trend. A poor conductor of heat and electricity. Well, it just talks about electricity, but heat also. That is characteristic of nonmetals. Dull. Dull means not shiny. Lustrous means shiny and reflective, but if it's dull, that is indicative of a nonmetal. And then we have one more here. Let's see if I can kind of pull this up so we can see this last one. I guess it kind of cut off on the screen. I can't get it to move, but it says gain valence electrons to form anions. So an anion is a negative ion. So if you look at that, these are the ones that form negative ions, -1, -2, -3. So the anions, that's going to be non-metallic. Okay, elements that have similar properties to the element bromine. Well, let's take a look. Here's bromine. Ones that are going to have similar are going to be the other halogens, the things in the same group. And so those are going to be things like fluorine, chlorine, iodine, astatine, stuff like that. Why? They're all in the same group. The halogens, they all have 7 valence electrons. We've talked about valence electrons several times. I guess we need to know what it is and why it's important. So these are the electrons found in the outermost energy level. Why are they important? It basically it tells how reactive an element is. List the common charges for the representative elements. So basically everything in the first row is +1, or first column. Second column is +2. Group 13 is going to be +3. 14 is going to be 4 plus or minus. And then when we get over here, this is going to be group 15. These tend to be 3 minus, 2 minus, 1 minus for group 17, and then group 18, the noble gases, have no charges. Notice the ones in the middle, they're not included. Most of them are going to have a charge of 2 plus, sometimes 1 plus, sometimes other numbers. They have various charges, but these tend to be fairly representative.